All right, good morning, everyone. We're going over Lab 3, Population Ecology, looking at the different relationships between predators and prey, and going through Simutext again, where this is our second and last time using Simutext. Again, you'll go into your breakout rooms and do 3 different sections. But first, some concepts or an overview of what we're going over today. We're first going to go over a couple of different growth models. So the exponential growth model, some background on that, comparing the exponential growth model to the logistic growth model. And then we're going to look at growth limiting factors and carrying capacity. So different variables that can be applied to our growth models and make a difference in their final shape or curve along the model. And then using everything that we've learned and the definitions that we've learned through these different growth models and limiting factors, we're going to go and do a simulation and look at a case study, which is Royale, through Simutext at the end. And I will go over more of that later. But I think you guys all have a pretty good idea of how to use Simutext after using it last lab. So I don't think this lab is going to be there's not a lot of functions that are different. But first, going over some concepts or learning objectives for today, we're going to explore the differences between exponential and logistic growth models. What does that mean in terms of population ecology, and species as they grow, and understand the factors that affect an ecosystem's carrying capacity. So what does carrying capacity mean, and what can limit their growth? First, population ecology is the study of changes in size and composition of population. So whatever we're studying, whatever we're looking at, what are the different, in the study area, what are the different species within our case study, and what are the different amounts of species, and how does that affect each other, as well as the factors that affect these changes. So in terms of space, resources, and all of that, how does that change our population? So first, if we're looking at exponential growth is a population increasing at its maximum growth and slowly increases in size at first and accelerates really quickly. So the result is a J-shaped curve. If we're looking as an example, if we're going to refer to 2020, the start of COVID, we can look at this graph where on our Y, our vertical axis is the amount of confirmed COVID-19 cases over time. So we're just looking at the first couple of months of 2020 before, and then right at the beginning of when COVID started. So we can see that from around mid-January to the beginning of March, there weren't really any cases. But then as COVID was introduced, more confirmed cases started popping up. And slowly we can see that exponential growth, that curve starting to happen, where the amount of cases started increasing and then really quickly started increasing more towards the middle and creates this J-shaped curve. So if we're thinking about this in terms of hosts, we can also say that once we have 1 confirmed COVID cases and as it starts to spread, as long as there's unlimited resources as an unlimited host, it's going to spread exponentially, because they have it's right in the beginning when there's a lot of resources available and there's nothing really stopping the growth of COVID at this point. So exponential growth can be used, or there's an equation for exponential growth, and exponential growth is also continuous population growth in an unlimited environment, which can be expressed as this equation. So our dn dt is instantaneous change with respect to time, and that's our growth rate, is equal to R max, which is per capita intrinsic rate of increase, multiplied by population size. So looking at this equation, as our population size, our n, increases, the rate of our population increase is going to also get larger. So how fast our population grows, our rate of change would increase as our population increases, which makes sense. But we can't really use this equation for a long time because it doesn't define reality. In real life, there are limitations to growth. So we can refer to this equation in the beginning when we're still looking at a population as it's starting to grow, but it can't really use for long periods of time. So exponential growth, the larger the population size, our n, the higher the population growth rate, our dn dt. Some assumptions, though, about exponential growth is that we have unlimited resources. We have unlimited water, unlimited food, unlimited hosts, things like that. There's also, assumptions, unlimited space. Also, we're assuming with exponential growth that there's no predators, nothing to control your population or your species as it's growing. And we're also assuming that there's no environmental impacts or changes. We're assuming that climate change isn't happening. We're assuming that, say, if you live on a coast, sea level rise isn't happening, so that's not affecting your infrastructure or the agriculture in the surrounding area or how well you grow your food in that area. Or even with climate change, as your environment's starting to change, say for certain bird species, their livable habitat up a mountain could only be a certain temperature, but as climate change changes that environment and raises the temperature in a certain area, their habitat's starting to change and it might eventually go somewhere else. So some assumptions for that is that environmental impacts, climate change isn't happening for exponential growth. Now, compared to logistic population growth, now we're starting to look at carrying capacity. So, and also factors that can start to limit your growth. So on the N, again, on the vertical axis is your number of individuals. So however many species, however much your population is growing all over time on your horizontal axis. And now we are taking into consideration K, which is our carrying capacity. And this is our theoretical maximum population. So we can see that through logistic population growth, our population starts to increase almost in that J-shaped curve from exponential growth. But growth starts to slow down near our K, our carrying capacity, as it starts to encounter different growth limiting factors. So that's when it's going to start to stabilize around our carrying capacity at around our K, and then it's going to reach that K. Unless other variables come in, it's going to stay at this K carrying capacity. So it's going to logistic population growth. When we're taking into consideration factors that limit our growth, it results in a sigmoidal or S-shaped population growth curve. So in the exponential growth model, it was that J shape, and in our logistic growth model, it was that S shape. Our logistic population growth, again, as resources are depleted, population growth rate slows and eventually stops at our K, our carrying capacity, and results in this S sigmoidal population growth curve along our model. More specifically, carrying capacity is the maximum number of individuals a population can sustain or an environment can sustainably support. So at that line on our graph, our K, our carrying capacity, and this depends, and this relies on the fact that there is a finite amount of resources in a system that can only support a finite number of individuals. So we're now taking consideration, and now we know that there's not unlimited resources, and there's only so much that our population or our species can grow up to. So more specifically, factors that affect carrying capacity are K, availability of resources, again, food, hosts, water, things like that. Space too, the amount of space that your population can spread out and inhabit. And it's also availability of resources is also affected by the climate. Say it could be seasonal, like a short, normal, or long growing season can affect how much resources you have, but also as our climate is changing, that could affect our growing seasons and what's available to us too. Another factor would be predators. we're assuming that we're not looking at predator. If we're looking at prey populations, predators would depend on the prey population and also limit prey population. But if predator population, if we're looking at the growth of the species, then the more prey that the predators have access to, the higher their growth. Now, referring back to COVID and how we went over it for our exponential growth model, now if we're looking at it on the logistic population growth, we can see that if we're looking a couple more months or like another month in the beginning past March, that as we thought that in the beginning that there was that J-shaped curve, that exponential growth, but slowly it's starting to hit that K at that point, that K carrying capacity, where it started to run into as availability of resources, as the amount of hosts started to lower because people there, that's when the stay-at-home order started happening and the more people are starting to wear masks and social distance. And so less hosts are becoming available, and we start to see a leveling out at that point, the K. So again, as hosts start to not be available, there were less people to spread COVID to. And that started to create this S-sigmoidal curve. Now, how we saw with our exponential population growth, there was an equation for that. We now have a logistic population growth equation, and it's basically the same thing. All we're adding is this parentheses, these factors multiplied by our original equation. And we are now just taking into consideration our K, our carrying capacity. So that's the only difference between that equation and this equation. And so as population size, as our N approaches carrying capacity, the fraction on the right-hand side of the equation becomes smaller. So as our K, whatever number of individuals within our population, as it gets to that K on our carrying capacity, then the equation or this right-hand side, these factors start to get smaller, and we can see that our growth rate also starts to slow down. And that makes sense because we saw in our growth model, when we chart it out, we can see that S-sigmoidal shape as it slows down near our K, our carrying capacity. Now, with all of these definitions and concepts, we are going to look at Isle Royale in Michigan, USA. So Isle Royale is this island, small enough for scientists to study for a long time. It's the longest running ecological study of different predator-prey species. This island, in the beginning, it was just shrubs and vegetation. And then from the coast, moose started to swim over. Moose are really great swimmers. They started to swim over, started populating this island. And then within that, I think within a couple of decades, their population started to stabilize. And then wolves were introduced. And between those different species of vegetation, moose, wolves, there was an interesting dynamic where, again, because it's such a contained study area, it was easy for ecologists to see the population growths and then measure what would the differences be between growing seasons and things like that. And now we're going to look at Isle Royale through our simulation, through Simutext. So again, we're looking at more specifically moose and wolf populations and how do they affect each other in Isle Royale. But how did wolves get to Isle Royale? So one really harsh winter, there was a lot of snow, an ice bridge formed from the coast to Isle Royale, and wolves crossed that bridge, found that in the middle of this winter, the moose didn't really have a lot to eat, so they were slow moving, so they basically had a lot of moose to eat, and that's how wolves were introduced to Isle Royale. And that is the very basics of this case study. And now you are going to be looking at the populations between these two species through Simutext. So let me just share my screen with Simutext. One moment. Okay, so when you go into Simutext, in the front page, we already went over understanding experimental design last lab. Now we're going over Royale. So if we just click into Royale, it will open up for us. And we are given this front page for Royale. And if we click next, we can see in the context that there is contents, that there are 6 sections. We're going over the first 3. So the first section is, so actually I'm going to be putting you all in breakout rooms to go over these 3 sections. The first section, I'll be giving you 20 minutes to go over when the moose arrives. So just looking at the moose population, how would the moose population be affected by? You're going to be playing around with the simulation. Then we're going to come back to the main breakout room. And then I'm going to look at everyone's progress and answer any questions that you have, and then introduce section 2. The wolves arrive, and that's another 20 minutes in your breakout room. And then we're going to come back and I'll introduce our final section, section 3, changes in weather, where we're looking at the differences between short, normal, and long growing seasons, and just seeing how our populations change because of that. So as an introduction to section 1, to when the moose arrive, if we just click next, we're given some background information in the beginning, which I briefly went over. You can read it through, but basically there's talking about the beginning when moose started to arrive and how, excuse me, and how wolves were eventually introduced after a couple of decades. And it was a small enough, it's the longest running study for these type of population dynamics, and we are now going to look at it through the simulation. There, in the third slide, we can click on different buttons to get background information on different species like grass, fir, sugar maple, and moose. And when we click on that, we're just going to answer a couple of questions about these organisms. But if we go on to the next slide, that's when we're going to start looking at our simulation. So our simulation, it's going to introduce moose on its own at first. So say we're going to play the first 5 simulated years. So first in the beginning, at this chart down here, we have our go step to just start our growth. And we can also stop this growth. And then these different steps at the bottom, step 1 or step 50, it just means when you click on it, it'll add 1 year of growth, or it'll add 50 years of growth. Say we wanted 5 years, we'll just click this button 5 times, it'll grow. We can also change the speed of our growth by this scroll tool at the bottom, where we can drag and click and make the population grow faster or slower. And we can also, at the top corner of our chart, zoom in and out of our study area. You can see around year 7 that the moose have started to arrive and started to eat at our vegetation. But let's also, let me introduce the next slide, where we would want to, I'll just go over this first slide too to show how can we look at how many mooses on our island at a given time. So let me just reset our population, and we're going to want to run our simulation for 50 virtual years. So we'll just click this button. We can see on the overview, that's our moose population is starting to explode. And then at this point, it's starting to level out starting to stabilize at what we can see. It's almost like our carrying capacity, our K. So now it'll stop after 50 virtual years. We're going to look at our population graph and see what's the approximate size for this first question. What is the approximate size of the stable moose population, so our K? And if we wanted to see how many moose is in our study area, we can just click and scroll along this line. Since it's the approximate size and it's not, there's a range, we can say that maybe it's around 570. And we can check our answer. Since it's approximate, it doesn't have to be super exact, so that's correct. And same thing, if we wanted to see what's the maximum size of the moose population, we can just click and drag along and say in our maximum, in our first growth, we have around 850 moose. And we can just check our answer for that. So moving on, if you also needed to add more moose, there right next to the binoculars tool, there's this add this plus moose button. If you click on that, you can just click and drag a square and add like however many moose that you need. And instead of clicking one by one and adding one moose at a time. So that's the basics of section 1. I will now put you in your breakout rooms, but did anybody have any questions before we move on? Okay. Okay. So I'll give you all around, say, 20 minutes. 20 minutes to do section 1. I'll check in near the end to see everyone's progress and just talk you through any questions. So I will see you all at around, let's say a little bit more than 20 minutes. Let's just round it up to 8 or 9:15. I will see you all in a little bit.